morning. Yeah. In the last class, we have seen classical process synchronization problems like we have seen bounded buffer problem, then readers writers problem, then dining philosophers problem. Okay, basically this dining philosophers problem is like we will be having round dining table, and we are having philosophers around the table. We are having 5 philosophers, namely 1, 2, 3, 4, 5. Okay, these are the philosophers, and what is the work they will be doing is either they will be thinking for some idea, or they will be eating. Okay, only two things they will be doing. One is they will be thinking, another one is they will be eating. Okay, these are the two things they will be doing in general. Okay, other than that they will not communicate with the other philosophers. They will not communicate. This is what the context that we are considering. So how many philosophers we are having around this table is 5 philosophers we are having, and in order to eat whatever the rice here, it is already served into their plates. Okay, let us assume in order to eat this particular rice or some item, they need to get 2 forks. Okay, those we can consider as chopsticks. Okay, 2 chopsticks they have to get, so that this particular person, this particular philosopher could able to eat. Now you consider one. Okay, first philosopher is having 1 and 2 chopsticks. Okay, how many chopsticks we are having here around this table is 4. Sorry, 5. 1, 2, 3, 4, 5. So total 5 chopsticks we are having around this table, and for one, which are available, 1 and 2 are available. For 2, 2 and 3 are available. For 3, 3 and 4 are available. For 4, 4 and 5 are available. For 5, 1 and 5 are available. Now you consider, in order to eat, what you call, first philosopher to eat, he needs to get 1 and 2. In order uh, in order to eat second philosopher, he needs to get 2 and 3. Similarly, in order to eat fifth philosopher, he needs to get 5 and 1. Got it? Like this, two chopsticks he needs to get, then only he could able to eat. Okay, the assumption is they will not interact with their neighbors. Just they will try to sense whether chopstick is free or not. If both the chopsticks are free, then he or she could able to eat. That's it. And occasionally try to pick up 2 chopsticks, one at a time, to eat from bowl. Okay, from this bowl, if he gets 2 chopsticks, then he will eat. Okay, they need both to eat. Okay, both chopsticks they need to eat, and after eating they will release both the chopsticks. This is what the now setup that we have to consider. Yeah, next, here how many philosophers we are having? 5. And what is the shared data here? Bowl of rice. This is the shared data, of course, and it has been served here. Okay, don't consider this rice now as the shared data. Just you consider it is already given. Okay, this shared data is already given here, but what is the other resource that each philosopher requires? Chopsticks. Okay, next, as we are having 5 chopsticks, we are using, in order to maintain synchronization, we are using a variable called chopstick of 5. It is an array. Okay, and each cell of the array will be act as a semaphore. As we have considered, semaphore is nothing but an integer variable. So integer array we will be taking chopstick of 1, chopstick of 2, chopstick of 3, like this. For each chopstick we are creating, we are considering a semaphore. Okay, what is the use of semaphore basically? Yeah, anyone please tell me. What is the use of semaphore? Why we require? Yes. Yes, please respond, ma. Abhiram, what is the use of semaphore? Yes, you can send message also. Yes, please respond, ma. What is the use of semaphore? Why we will use semaphore? If we have certain common data, shared data, in order to keep this particular data to be utilized by only one process at a time, that is in order to maintain critical section, in order to handle critical section problem, we will be making use of semaphore as the integer variable. While entering into this critical section, every process needs to check the semaphore value, that is that integer variable value. If it is greater than 0, then only it will be entered into this critical section. While coming out of this critical section, it has to increment that semaphore value. By that, we could able to maintain mutual exclusion within this critical section. That is what the intention of using semaphore, isn't it? Yes. Yes, please respond, ma. Anish, Nitya, did we discuss about semaphore or not? Siddharth, yeah, okay, thank you. Here, the setup here is like five philosophers, and they needs to obtain two chopsticks to eat. Okay, this is the setup. Now, in order to maintain, it is like one chopstick cannot be obtained by, cannot be taken by both the philosophers at the same time, isn't it? So, how we could able to make this synchronization? Okay, is by making use of semaphores. We are defining five semaphores. Okay, each we are referring as a chopstick of I. That means for ith chopstick, we are making use of the semaphore chopstick of 5. Like that, 5 semaphores we are using, and we are initializing with the value 1. All these particular cells will be filled with 1. What does it mean? All the chopsticks are free initially. Whenever one particular chopstick has been taken by one philosopher, automatically that particular value will be decremented. Another one cannot choose this or cannot take this chopstick. That is the meaning. So now, whenever this semaphore value is greater than 0, then only he could able to enter into critical section. That means he could able, any philosopher could able to take that chopstick. If chopstick value, that is chopstick semaphore value is greater than 0, if it is 1, then he could able to take it. That is what the meaning. Now, if you implement this, how we can implement is like first, you consider this particular one. First philosopher has taken this first chopstick, then he has to try for second chopstick. Okay, he will take this, he will be seeing whether one is free or not. If it is free, then he will go to see whether two is also free or not. Okay, if these two are free, then he could able to start eating. Okay, that's what we will be having. You see here, ith philosopher will be taking I. Okay, now you consider I value as 1. Then chopstick of y, I. That means chopstick of 1, weight of chopstick of 1. So he will be checking whether chopstick of one value is greater than 0 or not. If it is greater than 0, he will take that. Then he will continue the next instruction, that is weight of chopstick of I plus 1 mod pi. What does it mean? I plus 1 is nothing but 1 plus 1, that is 2. 2 mod pi is 2 itself. So he will be waiting for second chopstick. Whenever he gets first chopstick and second chopstick, then he could able to eat. While coming out of, after eating, he has to um, put those two back on the table, so that another philosopher could able to utilize those chopsticks. So signal of chopstick of I, first he will be releasing this chopstick, then he will be releasing the other one as well. So just he is requesting, he is sensing whether these two chopsticks are free or not. If these two are free, then he will take it and he will eat. After eating, he will release both the chopsticks. That's it. This is dining philosopher problem implementation by using semaphores. Okay, what are the semaphores here? Chopstick of 1, chopstick of 2, 3, 4, 5. These 5 are the semaphore. For each chopstick, we are making use of one semaphore variable. That's it. It is like a doctor patient example which we have seen. 5 doctors we are having. We need to meet adjacent doctors like 1 and 2, first doctor and second doctor. For every doctor we are having a lock. What is that lock? Chopstick of I. For ith doctor, chopstick of I. Like that we are making use of the lock, that is a semaphore. So after getting both the locks, he could able to meet doctor, and he can come back to, he can come out of the room. This is what the setup. Now what will happen here is, so let us consider in this particular example, one has yeah. Now you consider philosopher 1 has taken the first chopstick and he is waiting for the second one, but second one has held by second philosopher. Next, third one has held by third philosopher. Fourth one has held by fourth philosopher. Fifth one held by fifth philosopher. What is required for fifth philosopher to eat? Fifth chopstick and first chopstick. But first one is held by first philosopher. When he will release, whenever he gets the second one. But second one is held by second philosopher. When he will release that, whenever he gets third one. But third one is held by third philosopher. When he will release, whenever fourth one he gets. When fourth one will be released, if fourth philosopher could able to get fifth one. So it is like 5 is waiting for 1, 1 is waiting for 2, 2 is waiting for 3, 3 is waiting for 4, 4 is waiting for 5. So it is a circular waiting. Okay, due to this, what will happen is deadlock will occur. Why? Because this set of process, like philosopher 1, 2, 3, 4, 5, these are the set of process, will be waiting for an event within themselves, which will occur within themselves, then it will cause deadlock. This is the problem with this approach. You consider just a weight of chopstick of I means first chopstick he will get. After that he will be trying to get a second chopstick, but by the time philosopher 2 has executed the first one, that is weight of chopstick of 2. So second one will be held by second philosopher. So like this, it will cause circular waiting. Then this will lead to deadlock. Got this point? How we will be getting deadlock from this? Yes. Yes, please respond now. Yeah. Next, this particular deadlock can be handled in several ways. Like at most 4 philosophers can, we will allow only 4 philosophers to sit around the table, so that we will be having 5 chopsticks. At least one philosopher will be getting one philosopher will be getting 2 chopsticks. So he could able to complete. After that, we will be left with what you call five chopsticks and three philosophers. So another process, another philosopher could able to eat. Again, we will be getting five chopsticks and two philosophers. One of these could able to complete eating. Like that, if you allow only four philosophers to sit on the table and five chopsticks, then at least one philosopher could able to get two chopsticks. This is like, if you remember, pigeonhole principle. Did you heard of this pigeonhole principle? Yes, pigeonhole principle. Yes or no? It is like, we will be having pigeonholes. Okay, let us consider five pigeonholes we are having and six pigeons we are having. We have to fill these six pigeons into five pigeonholes. Then it is evident that at least one pigeonhole will contain more than one pigeon. Yes or no? These are the pigeonholes. Okay, five pigeonholes we are having and six pigeons we are having. Then at least one pigeonhole will contain it more than one pigeon into it. Okay, this is pigeonhole principle. Although it seems naive, it will be used to prove lot of what you call big things. Yeah, if you remember this, then it will be simple to you. Like this was there in discrete structures. You might have learned in previous semesters. Yeah. So based upon that, we can have one deadlock handling technique. Another one is whenever both are available, then only a philosopher is allowed to pick the forks or chopsticks. Whenever both chopsticks are available to take, then only he will take. He will not take one and he will not wait for another one. Understood? Why deadlock is being happened is he is picking one and waiting for another one. He is trying to pick another one. By the time that is being picked by another philosopher, because of that deadlock is being happened. That circular waiting is happened, then deadlock is occurring. But in this approach, whenever both sticks are available, then only he is allowed to pick the chopsticks. Okay, this is another approach. Next, this is another solution that odd numbered philosopher pick the left chopstick first. That is 1, 3, 5 needs to pick one. Third philosopher needs to pick three. Like that, we are allowing only first one as the left chopstick for odd numbered philosopher. For even numbered philosopher, he needs to pick right chopstick. That means for 2, what is the right one? Right one is 3. So by the time if 3 is free, then only he will pick. Otherwise, he will not pick any chopstick. So that we can avoid circular waiting. This is another solution to handle this deadlock. Okay. Next, till now we have seen several problems and several approaches to implement the process synchronization, mutual exclusion, or giving the solution to the critical section problem, all these things by making use of semaphores. We are having two types of semaphores, binary semaphore and counting semaphore. Binary semaphore will be having the values 0 and 1. Counting semaphore will be having the values in unrestricted domain, like we can have any values. We can have even negative value also for counting semaphore. If negative value is that, those many number of process are being waiting for on that particular semaphore, that it will indicate. Next, whenever you consider counting semaphore, P and V operations we have seen. P operation is nothing but wait operation. V operation is nothing but signal operation. So P operation means the semaphore value will be decremented. V operation means semaphore value will be incremented. So you may get a question like semaphore value is so and so. Then after performing these many P operations and these many V operations, what is the value of semaphore? Then just you have to decrement those many number of P's and increment those many number of V's. That's it. To the initial value of semaphore, then you will be getting what is the current value of the semaphore. Like that you may get some questions. Even in gate exams kind of thing also you will be getting these questions I mentioned earlier as well. Yeah, due to this by using these semaphores we could able to make process synchronization. Okay, but there exist several problems even when we use semaphores. Why? Because here whatever the procedures we are writing, like here weight of mutex, then we are doing like this, then signal of mutex, weight of rw mutex, these all things will be done by programmers only. If programmer has what you call misused this opportunity to make process synchronization, to work with process synchronization knowingly or unknowingly, then what will happen is like suppose weight of mutex should be followed by signal of mutex after coming while coming out of the critical section, but if he does not give signal of mutex, then process will be keep on waiting. Okay, it will lead to indefinite waiting, that is starvation. That is the problem, that is one of the problems. Or you consider another problem, like weight of mutex should be followed by signal of mutex. Instead of that, signal of mutex is used first, then weight of mutex. What does it mean? Mutex value will be incremented then decremented, and so whenever we give signal of mutex, the value will be incremented. So it will lead other process to held the to enter into critical section. So it will allow more than one process to be in critical section. Other problem can be like signal weight of mutex, signal of mutex. This is a sequence in general, but instead of that, if he gives both as a signal of mutex, signal of mutex, then what will happen is the semaphore variable value will be incremented twice. So which will lead to more than one process to be in critical section again. So this is a synchronization. This will lead to serious synchronization problems. So these are the some of the difficulties that we have with the semaphores. In order to overcome these problems, like these are the problems: signal of mutex, then weight of mutex. What is the correct sequence? Weight of mutex followed by signal of mutex. Okay, in between weight and signal, we will be having critical section code. Okay, this is one of the problems. Next, another one is weight of mutex, weight of mutex. That means we are in weight, we will be decrementing the mutex value. And again, if you don't give signal value while coming out of the critical section, again, if you call weight, then what will happen? Again, that mutex value will be decremented. If it is already less than or equal to 0, then it will keep on checking. That means although it has completed the critical section, what will happen? It will keep on waiting. That is busy waiting, which we have seen earlier. This is another serious problem which will be caused by semaphore usage, incorrect usage of semaphore. Next, either weight of mutex or signal of mutex are both, if you omit, in the sense in your procedure, if you don't have weight of mutex or signal of mutex, what will happen? It will enter into critical section without checking, without waiting, or without sensing what is the value of the semaphore. Then it will lead more than one process to be in critical section. This is also the problem, another problem with respect to semaphore usage. So how we can overcome these problems which will be occurred due to semaphores is by making use of the concept called monitors. Okay, monitors. This monitor is nothing but abstract data type. Monitor is nothing but abstract data type, in the sense we will be having certain procedures, certain functions which are defined. Like monitor is the abstract data type. We can have certain name to it, and we will be having list of procedures, like procedure P1, then parameters, then the body, like P2 and the formal parameters and the body, like that. Pn, procedure 1, 2, 3, so on, n number of procedures we can have here, and all these procedures can utilize some shared variables which are declared here, and within the procedures, whatever the variables declared, those can be accessed by these procedures. Okay, Now this particular ADT abstract data type will be provided to the programmer, and he will not be writing the code directly. He will be utilizing only these particular procedures which are provided through this monitor. Okay, so that what will happen is he is not having access to alter this. So these problems can be avoided, that like signal of mutex, weight of mutex, these things will not occur. Whenever we have this kind of flexibility, programmer may use incorrectly, and it will lead to deadlocks or starvation problems. But if you provide monitor, what will happen, it is high level abstraction that provides a convenient and efficient or effective mechanism for process synchronization. Like we will be allowed to use only these procedures, that you keep in mind. We are allowed to use only these procedures. Through these procedures only we could able to access shared data. Through these procedures only we could able to make use of shared data. So that how shared data needs to be what you call modified, needs to be accessed, all these things will be defined in these procedures. So even though programmers allowed to use these procedures, they cannot modify the code within this. So mutual exclusion will be ensured, process synchronization will be ensured, deadlocks and starvation problems can be avoided. This is the solution proposed by using monitors. Okay, and what is the concept here is, at a time only one process may be active within the monitor. Like we'll be having a monitor, let us assume monitor as this particular box. Into this particular one we will be having several procedures, p1, p2, p3, so on, pn. And whenever a process has entered in this particular monitor, then no other process can able to no other process can be active within this monitor. So if a process wants to utilize this, okay, wants to enter into this monitor, then it has to wait in the waited queue. In the waiting queue it has to wait. Whenever a process has completed, then it will monitor from the waiting list, one of the process will be picked and it will allow. Okay, this is seems to be whatever the critical section or mutual exclusion which we have seen earlier, this seems to be same, but I will tell you where this will differ from the earlier one. The like semaphore, in the semaphore what will happen, try to listen carefully. In the semaphore we will make use of wait and signal operations, right? Wait and signal operations. What this wait operation will do, whether semaphore value is greater than 0 or not, it will be checking. Okay, if the semaphore value is greater than 0, then it will enter into critical section. While coming out of this, it will increment the, that means it will make use of a signal operation. That means it will increment the signal what you call semaphore value by 1. So after decrementing the semaphore value, it will enter into critical section. While coming out of this, it will increment. This is usual procedure that we will be having in semaphore. In the case of binary semaphore especially, if it is greater than 0, then it will decrement the semaphore value and enter into critical section. If it is less than or equal to 0, then it will keep on waiting. That is the procedure of wait. Similarly, signal operation means just it will increment the semaphore value. So from 0 to 1 it will come. Okay, now you consider there exist several process, like P is one process, Q is another process, R is another process. Now P will sense what is the semaphore value. P is executing wait operation. What is the semaphore value? 1, let us assume. So it will enter into critical section. So P is in critical section now. Next, while coming out of the critical section, what P will do? P will execute signal operation. So signal operation means semaphore value will be incremented by 1. So P will come out of it. Then by the time Q and R will be waiting. Q and R both will sense what is the value of semaphore. Both will sense that the value of the semaphore is 1. So both will try to enter into critical section. This is the problem. So it may result that both the process can enter into critical section at a time. This is the problem. So how we can avoid this is, here in the monitor, only one process at a time can be active. So now whenever one process which is active in the monitor that has completed its execution, then it is coming out, then it will give signal operation. Usually in signal operation of the semaphore, what we will do, we will increment the semaphore value so that more than one process can enter into critical section. This is the problem here. But in this monitor, what it will do is, whenever it gives a signal, only one process can be active again. That is the thing. Whenever it is coming out of this monitor, it has completed execution, then only one process can utilize that signal call. Whenever it gives a signal, then that can be utilized by only one process, so that at a time in the monitor only one process can be active. That can be ensured here by using this monitor. Okay, this is the difference from semaphore and the monitor. Yeah, this is the pictorial representation of the monitor. Here this entire thing is the ADT. Here we are having some shared data. Next, procedures which we have seen, like P1 is one procedure, P2 is another procedure, like that, so on, Pn number of procedures we can have. So these are the procedures. By using these procedures only, we could able to perform any critical section operations. Only these procedure calls are allowed by the user, can be utilized by the user. He cannot write his own code. Okay, that is what being ensured. Next, in order to start this particular one, we are having some initialization code here. That's it. Now whenever some process wants to enter into this monitor, then those all will be kept in queue. Okay, according to the signal operation, whenever one particular process has given the signal operation, only one of these processes which are in queue will be active and will be entered into monitor. This is the operation of the monitor. Yeah. Next, there exists one special type of variable called special type of course integer type of variable only, but that particular one we call it as condition. A condition is the type of the variable. These type of condition variables we can declare within the monitor. This is the primary difference between the semaphore and the monitor. In the monitor we can have several variables of type condition, whereas in semaphores, when we use semaphores, we will not be having these kind of condition variables. What is the use of condition variables is, on one particular condition variable we can make several processes to wait. Like here we are having queue, right, entry queue. So we can have separate queue on one particular condition. Like I will show you another. Yeah, here you see we are having two conditions, x and y. X is having separate queue, y is having separate queue. Whenever a signal is given on x, then corresponding queue, from the corresponding queue, process will be selected and it can enter into the monitor. This is what we can ensure. It is like earlier we have seen several semaphores we can have. For each semaphore we can have blocked list of process. Similar to that, here we are having conditions. Okay, these conditions can be utilized to make corresponding process to wake up. Okay, that is what the usage of condition variables. And here two operations are allowed on a condition variable. One is wait, another one is signal. See here the difference between wait operation, signal operation, which we have seen in semaphore and in this monitor we will be seeing, then only you could able to understand. Otherwise it looks like almost the same. Here the wait operation will invoke the operation is suspended until signal operation. A process that invokes the wait operation will be suspended, straight away it will be waiting, and whenever it gets a x dot signal, then only it will wake up. Okay, it will be active. That is wait operation. Earlier it was not like this. Like when we use a semaphore, wait operation will check what is the semaphore value. Okay, what is the semaphore value? If it is greater than 0, it will enter into critical section. If it is greater than less than or equal to 0, then only it will be waiting. But in the monitor, whenever we say x dot wait, it will be waiting until it gets the signal call. Okay, it will be suspended until it gets x dot signal. Okay, this is the difference between wait operation in a semaphore and wait operation in monitor. And another main difference here is signal operation. In general, signal operation, what uh, how it will be executed in semaphore? It will increment the semaphore value. Just it will increment the semaphore value. This is what the functionality of signal operation in semaphore. But here x dot signal, in the sense, it will resumes one of the process. Try to understand here, only one of the process which are suspended will resumes its execution. That is what the signal operation. Suppose you consider monitor we are having, and there exists x, and this is the q. For x we are having the q. X dot wait means one process will be kept in waiting state. Okay, in this particular queue. Next, x dot wait, again it will be kept in the queue. X dot wait, again it will be kept in the queue. Now one process has completed its execution. Let us say t has completed its execution, then it has given signal operation. So monitor is free, then one of these process only will be resumed, either p or q or r. Only one of the process will be resumed. That is the operation of wait and signal operation in monitor. Wait operation in semaphore will check whether semaphore is greater, the semaphore value is greater than 0 or not. If it is greater than 0, then it will not wait, it will continue to enter into critical section. Whereas in monitor, irrespective of the value, it will not check any value, just it will while performing this x dot wait, it will be kept waiting. It will be in what you call queue. Okay, in this particular queue it will be kept by suspending. That's what the wait operation. Next, signal operation in semaphore will increment the semaphore value, whereas in monitor, signal operation will resume one of the process which were suspended earlier on this particular condition. Okay, x dot signal means corresponding process only can be active. Suppose you consider there exist two conditions, x and y. Conditions are nothing but a type of the variable. Okay, x is one condition, y is another condition. So y dot signal means only in the process which are waiting here in this queue. Out of these, one of the process will be resumed. That is the operation of signal. Suppose let us consider we are having this queue as empty, and we have given y dot signal. Try to understand, why queue is empty, that is no process is being suspended. Then also y dot signal has been given. That means what is the operation of signal? One of the waiting process on that particular signal should be resumed, but we don't have any process. But on x we are having some process to some process in suspended queue. Although y dot signal is given, no process are waiting on this particular condition, so nothing will be happened. This particular signal call will be ignored. That's the difference between especially the signal operation in semaphore and signal operation in monitor. Whenever signal operation is given, if any process are waiting in the queue, one of the process will be resumed. Suppose no process is waiting, then simply this signal call will be ignored. Understand this this point? Like you consider x dot signal resumes one of the process if any. Okay, if any process waiting, by giving the x dot wait, then though out of those one of the process will be resumed. Suppose no x dot wait on the variable has been invoked, then no process is waiting, right? No process exists in the corresponding queue, then it has no effect on the variable. Just it will ignore this signal call. That's it. This is about the condition variables. Condition variables are nothing but just the integer type of variable, but the operation that we can perform on these condition variables are wait and signal. Wait operation will make the process to kept in suspended queue, and signal operation will make one of the process to resume if any. If no process is waiting, then it will ignore that signal call. Got it? So now you can consider in this x is one condition, y is another condition variable. Whenever x dot signal has given, one of these three only will be resumed. Okay, y dot signal given means one of these two will be resumed. After that, y will be waiting for, y will be having the suspended queue with one process. Again, y dot signal given means this process will be resumed. Now y is on this condition, no process is being waiting, okay, is being suspended. Then y dot signal again given, then what will happen? It will be ignored. That is what the operation of monitor with this condition variables. Yeah, is this clear? Any doubts so far? Yes. Yes, Bhargav. Okay, next, this condition, if a process invokes x dot signal and process q is suspended in x dot wait, then what should happen next? Try to understand. P has given x dot signal and q is suspended, process q is suspended in x dot wait. Then what will happen? It will resumes q, right? Why? Because P has given x dot signal. What does it mean? One of the wait suspended process can enter into monitor. So both q and P can enter, but in general, those that is not allowed, isn't it? Both q and P can enter, but that is not allowed according to mutual exclusion. So whenever q is resumed, q is resumed, then P must wait. Okay, while waiting for it, whenever it has given signal, then we are having two options. One is a signal and wait, another one is a signal and continue. Signal and wait in the sense, P will give signal operation. Okay, P will execute signal operation and waits until Q leaves the monitor. That means whenever it gives a signal, automatically Q will enter into monitor. Until Q leaves the monitor, it has to wait. Okay, this is one of the options P has. Or P has to wait for another condition. P has to wait for another condition to give signal. Okay, this is one of the options that P has. Next, another option is signal and continue. In the sense, P will give signal. Okay, x dot signal invoked by P, but Q will be waiting until P leaves the monitor, or Q will be waiting for another condition. Like you consider, we are having two process P and Q, and this particular P is being waiting on x dot wait, okay, and this is also waiting on y dot wait as well. Now Q has given the signal, x dot signal has been given. X dot signal means P could able to resume, but in order to do that particular one, P needs another signal to get. Okay, P needs another signal, so Q could able to wait until P leaves the monitor, or it has to wait for another condition. That is the second alternative. If another condition needs to be on another condition, if it needs to get a signal, then Q has to P has to wait for it. Okay, there are two options: signal and wait, signal and continue. Whenever P invokes this X dot signal. Here I have given in reverse, like Q has given the X dot signal, then P may be waiting, or you consider in this particular way itself, like P has given X dot signal and Q is suspended on X dot wait. Then in general, Q will be resumed. Straight away, Q will be resumed. But Q may be, P will be having several alternatives, like P may be waiting until Q leaves the monitor. This is a straight option, or it waits for another condition. If P gets another condition, on another condition, this what you call, it is in a suspended queue, then it will be waiting. Okay, that is a signal and wait. Next, signal and continue in the sense, Q will be waiting until P leaves the monitor. Okay, whenever P is inside the monitor, Q cannot wait, Q cannot enter, so Q will be waiting, or Q will be waiting for another condition to give signal. These are the two operations, and both the approaches will be having some pros and cons, and these are implemented by using a concurrent Pascal as what you call a hybrid approach. Like both the approaches they have implemented in some compromised way in concurrent Pascal language. Okay, that is a P executing signal immediately leaves the monitor. Whenever it executes the signal, immediately it leaves the monitor, so Q can be resumed. Yeah. So this is about monitors, and this is the solution given from the given for the problem called dining philosophers problem, which we have seen earlier. What each philosopher will do, either he will be thinking or eating. Okay, here by analyzing this particular one, while thinking he will not be bothering about eating, but for eating he needs chopsticks, right? Two chopsticks he will be needing. Okay, he needs sorry, he needs two chopsticks to eat. So while he wants to eat, he has to wait for some time. Okay, whenever he wants to eat, that state we are defining as hungry. He may be he will be hungry, but he will not be eating. Okay, so these two are different. Try to understand here. In general, they will, each philosopher will be doing two things. One is thinking, another one is eating. But in between these two, if he don't get chopsticks, then even though he is hungry, he will be waiting. So that is a hungry state. So we are defining a new data type called state. Okay, state, and it is having three values, either thinking or hungry or eating. And as we have defined condition as the variable, we are defining 5 variables of this particular type condition. And just you consider monitor in the sense what we have what you call discussed with respect to monitor. Monitor in the sense it is an abstract data type where we will be having list of functions. Similar to that, here also we will be having a monitor. Okay, this is the monitor of dining philosophers. Here list of functions, list of procedures will be having. One is pick up, another one is put down. Pick up in the sense whenever state is hungry, then pick up. He will be calling this pick up, and test. What is this test? Will be saying, and after that, if he is not eating, then he will be waiting. If he is eating, then he will not wait. Otherwise, he will be waiting. Okay, what is this test? Will be saying. Well, pick up what he has to. When he could able to pick the both the chopsticks, whenever. What's the strategy is like one philosopher we are having. Whenever both of his neighbors are not eating, he could able to eat, isn't it? If he is eating, one of his neighbor is eating, then he cannot take this one. Suppose he is eating, he cannot take this chopstick. Suppose both are not eating, he is not eating, he is not eating, then he could able to eat. So that's what we will check here. That is in test we will be having. With respect to I, we will be checking state of I plus 4 mod 5. That means adjacent one. Okay, one of the adjacent one. Next, state of I plus 1. Suppose I is the philosopher, then I plus 1 is nothing but the beside one, this right side one, and the I plus 4 in the sense left side one. If both are not eating, try to understand, if both are not eating and he is hungry, this I philosopher is hungry, state of I is hungry, and state of I plus 1 mod 5 is not equal to eating, and state of I plus 4 mod 5 is not equal to eating, then he could able to eat. So state of I is eating. Okay, this is what we will do in test, and he will give the signal saying that another process could able to utilize. That means after eating what will happen, he could able to give chance to other philosopher. So that's what here we are doing, state self of I dot signal. By using this signal, if any other process, any other philosopher is waiting for this particular chopstick, he could able to get this chopstick, and he could able to resume eating. That is what the test process. So now pickup operation is to pick both the chopsticks whenever those are free. Okay, as we have seen earlier, deadlock can be avoided in several ways. That is, only 4 philosophers are allowed to sit. That is first approach. Second approach is whenever both chopsticks are available, then only he is allowed to take any chopstick. So this is based upon the second approach. That is, he will be sensing whether adjacent philosophers are eating or not. If both are not eating, then only he will be allowed to eat. Okay, that is pickup. Next, after eating, he has to put down both the chopsticks. That means state of I will be thinking. After eating, he will be in thinking state. Then test of I plus 4 mod 5, test of I plus 1 mod 5. That means for both the what you call neighbors, we will be giving the signal. Accordingly, he will be for this particular neighbor, we will be checking whether both the neighbors are not eating or not, and he is hungry or not. We will check. Accordingly, we will give chance to that particular neighboring philosopher as well. Okay, this is about dining philosopher problem solution by using monitor. And the main thing that you have to understand here is whatever the procedures here we have, pick up, put down, and test. These all are the procedures. These only can be accessed by programmer. They cannot define these on their own, so that that process synchronization can be ensured, deadlock can be avoided. That is the advantage of using monitor over semaphore. Is this clear? Like these procedures are fixed, they cannot alter, so that whatever the earlier states we have seen, like signal mutex or wait mutex, like this, whatever the incorrect use of semaphores will not occur in monitors. That is the main advantage of using semaphore vertical monitors. Yeah, next we will be seeing other topics in the next class. Okay.